So this video is going to just introduce the math formulas, the quantitative ways to solve for energy and all the variables associated with energy. I'm not going to do any actual calculations in this video, so if you already know the formulas and you're familiar with them, move on to the next videos. This one's just going to talk about the variables and the equations themselves. So in order to do all of this, basically everything goes back to those heating and cooling curves. And if that's something that you still don't feel fully comfortable with, I strongly encourage you to go back and watch that video first, because I'm going to be referring back to the curve. And if you don't know what the heck I'm talking about, then it's not going to make very much sense. So here is, okay, that's nice. It's a little curvier than I intended. Hang on, let me fix it. Probably should have had this done before I started, but that's okay. All right, so here we go. We're gonna say that this is the heating curve of water. So here I have 0 degrees, here I have 100. We know that we can separate the curve into different regions. And within those different regions, we know that all kinds of different things are going on. And we can calculate, we can quantify the amount of energy that's going into or out of a system by looking at these, each specific region. So we're always going to be talking about energy. Energy is noted with the variable Q, and the units are going to be in joules. So Q equals energy. In this case, we're going to be specifically talking about heat, and the units are going to be joules, or a capital J. When we're talking about energy, when we're trying to quantify it, we need to take into consideration the mass of the substance, especially, actually, no matter what, we're always going to have to take into consideration the mass. So M is mass, and the units need to be in grams. Now, the other piece of information that you need depends on which part of the graph you're calculating the energy for. Because, for example, the energy here is a different type of energy than the energy here. And if you think back to the heating and cooling curve one, if we have the temperature changing here, it's going from a negative number to 0. What kind of energy is happening here? We have energy being stored as thermal energy. So if we have thermal energy, that means the temperature is changing. So that's obviously something that we're going to want to take into consideration when doing our calculations. So this is a change in temperature. And to calculate that, we're going to do the final temperature minus the initial temperature, or T2 minus T1. And our units, we want to always be in degrees Celsius. So we have a temperature change, we have M, we have Q, and then we have what we talked about in the last video, which is the specific heat capacity. How much energy can this thing hold before it increases in temperature? So that's where that specific heat comes in that we talked about in the last video as well. So the C, the specific heat, let me just write that down, specific heat, SPECIFIC. Specific heat, its units are joules per gram degree Celsius, because it's how much energy goes into a system while increasing the temperature of 1 gram of a substance by 1 degree Celsius. So again, that just kind of shows you where those units come from. Okay, so we can take all 4 of these variables, this Q, M, C, delta T, and we get an equation that I like to call the MCAT. Q equals MC delta T, MCAT. See, MCAT. So we use the MCAT equation anytime we see a temperature change. I'm going to write it out because you don't know what delta is. So temperature change. So if we're looking at the graph, get my orange highlighter, anytime I see an increase in slope or even a decrease, it could be going down as well, right? Increase or decrease in slope means I am using the MCAT equation, no matter what, every single time. So pay attention to the words, pay attention to, the explanation, what's happening. If you see that there's a temperature change, MCAT is your equation that you're going to use. All right. So obviously, we're not always going through a temperature change. We might be doing something else, in which case we would have energy being stored as anybody? Phase energy, EPH. Great. So when the phase is changing, energy is still going into the system. However, the energy is being spent pulling those molecules apart, causing the phase change. So we can't use the same equation. We can't use the MCAT equation because the temperature is not changing. So instead, we're going to use still, hang on, let me get purple. Of course, we're going to still use Q because we're still talking about energy. We're still going to use mass because it matters how much we have. But instead of the specific heat and a change in temperature, we have this constant called the what is it? Which one? The HF. I did the bottom one, right? Yep. So we have the HF, which is called the heat of fusion. And this is used anytime we have a phase change, specifically if it's melting, which means a solid is going to a liquid, or if it's freezing, meaning it's a liquid going into a solid. And going back to, just real quick, going back to our exothermic, endothermic from the last video, if we have something melting, something is melting, meaning heat is going into it, right? Because it's going from a solid to a liquid. It's a solid is cooler temperature, liquid is warmer temperature. So heat's going into it. If heat's going in, that's an endothermic exchange, and we're going to have a positive Q value. Boom, right there. If we have a liquid going to a solid, well, that's freezing. So that's taking energy away. So if I have my thing, energy is leaving it, and that would be an exothermic exchange, in which case our energy is lost. So we will see a negative value that represents that. So when you see the different signs, positive and negative, it doesn't mean like you have less than zero energy. Like that's not possible. You either have energy or you don't. The negative means the direction that it's going. So if you see a negative, it's exothermic, it's leaving the system again, and that makes sense because it's freezing. It has to decrease in temperature. So yeah, okay, so that's that. So that's heat of fusion. That's for this first plateau here. This second plateau, all the way up here, that's also an EPH. However, we can't use the same constant because when something freezes or melts, it requires a different amount of energy than it does to boil or condense. So again, we're going to have a third equation. Oh, I didn't even write the equation up here. Hang on, I'm sorry. So our overall equation here is Q equals MHF, where we have the energy equal to the mass times the heat of fusion. So super easy formula. Okay, so now going on. So again, we need Q, we need M, and then we need something called HV. And HV is the heat of vaporization. And again, we're going to use this formula when there's a phase change, specifically evaporating, aka boiling, or condensing. So here we're going to have a, if we're evaporating a liquid going to a gas, or a gas being turned back into a liquid. And again, we can ask ourselves, is it going to be, endothermic or exothermic? So liquid to gas, it's warming up, heat's going into it. So heat's going into the system. So it's going to be endo. And here, what color did I use up there? Green. So here we have it's decreasing in temperature, so heat's leaving, and that's going to be exo. And again, our formula, super simple, just Q equals MHV. So let me just zoom out here. Let's see how far I can zoom out. Okay, so we have our orange region. We have our purple region.